Hello, this is Jack Jackson. In this video, we're going to start a series of 3 videos where I'm going over some review exercises for the concepts in this playlist, or in the second half of this playlist. So this is Unit 2B exercises. When I originally had this unit set up, I had it set up as 1 unit, 2, hence the 1 playlist, Unit 2 playlist. But then I later on decided it was a little bit too long for my students, so I split it into 2 units, 2A and 2B. Earlier, when we got to the end of 2A, I had a set of review exercises over that portion. And now we're going to do uh, a set of review exercises over the second portion, Unit 2B. The Unit 2B exercises are over distributions. Um, Discrete distributions. So there are going to be 3 of these things here. And as with my review exercises at the end of Unit 1 and 2A, these are closely matched to the practice test, which is in turn closely matched to the exam for students who are actually in my class. So the first one here this one will go over the first 5 of these, and the next one will go over the next 5, and then the third 5. So there are 15 of these exercises altogether. Now, when you are looking at these exercises, um, you'll need to focus before taking the practice test. And so working through all the graded homework sets is certainly something I would encourage all my students to do. And then we have these review exercises. And the way these work is you'll be shown a screen that will have a problem, and I'll ask you to pause and work it yourself. And then only after you've worked it yourself should you go on to check your work against the following slide. I will go over the solutions in this video though. So when you're doing this, you should have your calculator, pencil, and paper out. And I allow my students on their exam to have a little note card of notes. You should probably already have that ready to go, so you can look up things on that. But at least your calculator and pencil and paper should be out ready to go. So you be sure to work out each exercise completely before going on to the following slide, where you'll see a solution with which you can check your answers and the process you use to get them. So if you watch the corresponding videos, this video, just be sure to pause the video and work the problems before going on to review the solution. It's very important you work them yourself. At this point, if you've worked through my slides and through my videos in this playlist, you will have done many exercises like these just in working through the slides, and then hopefully you've done some homework problems on those as well. And for my students, if you can master the problems in this review, then you should be able to work all the problems on practice test 2A and unit exam 2A. Make that practice test 2B and unit exam 2B. Okay, so without further ado, let's do the first one here. So here is a portion of a PDF CDF table. You're given all the values of the random variable x, and you need to fill out the PDF and CDF. So press pause and work it out yourself. Come back and check your answer in a minute. Press pause now. Okay, I hope you didn't have any trouble with this one. The first thing to notice is all the probability values of the PDF are the probability values that x equals this particular number over here. And they are all numbers that are between 0 and 1, and they must add up to 1. So if you look at this, let's see, 0.1 plus 0.3 plus 0.2 plus 0.1, that's 0.7. And so then the missing one had to be 0.3 for them to all add up to 1. Now the cumulative distribution function, the CDF, is the first one is the same here. The next one you get by adding these two up, the first 2 up. So that's 0.4. The next one you get by adding the first 3 up to get 0.6, or add the 0.4 to the 0.2 will do it as well. So 0.6 plus 0.1 is 0.7, or add these 4. And of course the last one should always be 1. So once again, let's remember what these things mean. For example, this 0.2 right here is the probability that x equals 7. Remember, a PDF is the probability that x equals that number. Whereas the 0.7 over here is the probability that x is less than or equal to the 11 over here. So CDF is a probability from forever left up to that point. Okay. All right, let's try another one. So here's a complete table for a PDF, and of course we could verify that. Notice that the probabilities are something between 0 and 1. And if we add those up real fast, let's see, 0.25 and 0.15, that's 0.4. Another one is 0.5, 6.7, three more is point. So that's 1, so that does add up. So this is a legit PDF. And of course the x's can be anything. Now what we want you to do now is find the mean and the standard deviation for this. Press pause now. Okay, well now you're back. Let's take a look. Well, there's a couple of ways we could go at this. We could actually work out all the details. I may do one of those in a minute. But if you have your calculator, say a TI-84 calculator, it's really, really easy to do this. You just go to your list. So go to Second, Stat, Edit, put your cursor on L1, hit Clear and Enter. Put your cursor on L2, hit Clear and Enter. And then type in the X values, 2, 5, 11, 17, and 22 into list 1. Hit Enter after each one. And then over here, put the corresponding PDF values. In other words, the corresponding probability values. 0.3, 0.2, 0.1, 0.15, and 0.25. And then you go to then quit. So that's second mode on a TI-84. Quit, and then press one variable statistics. And get that from going stat, right arrow to calc, and then it'll be the first one variable statistics. The list is the list of the x values. That is your values of your random variable. That's in L1. Get L1 by typing second 1. And your frequency list is in list 2. So type L2 by typing second 2. Not by typing an L and a 1 and an L and a 2 there. Second 1 and second 2. And then just press calculate. And it says X bar. It should actually be mu because it's like a population for a distribution. That is your mean of 10.75, and the sigma here is your population standard deviation right there. Round off to whatever it says, 4 decimal places. That's 10.75 exactly, and this is 8.19. See, that'd be 0.7. Okay, next. All right, here's the next problem. Translate each of the following statements into a probability statement. PDF of 3 equals 0.25, CDF of 4 equals 0.88, and CDF of 8 minus CDF of 3 is 0.41. Translate that into a probability statement. Press pause now. Work it yourself. Okay, hopefully you've worked it yourself. It's very important that you do that. Okay, so let's look at this. Well, the PDF is always a probability that x equals something. So this is the PDF of 3 is the probability that x equals 3. So this translates as the probability that x equals 3 is 0.25. CDF of 4 is the probability that x is less than or equal to 4. And of course that's 0.88 here. Now difference of two CDFs is a probability between things. Now we have to be a little careful here. CDF of 8 is the probability that x is less than or equal to 8. But at the same time, we want to subtract CDF of 3. That's the probability that x is less than or equal to 3 is subtracted. So what we really get is a probability that x is between 3 and 8, not including the 3, but including the 8. Now, if this is always true right here for what I just have said. Now, if this happens to also be a probability distribution that only takes on whole number x values, say like the main ones we've been studying, like the geometric and hypergeometric and binomial, then this would be the same as the probability that 4 is less than or equal to x, which is less than or equal to 8. But that's only true because there's nothing between 3 and 4 that has any probability. In general, what you have here is more correct, or is correct. All right. Explain what the situation is for each of the following families of distributions. So to be sure to explain all the assumptions, the meaning of the random variable, and the meaning of any defining parameters. This is going to take you a little bit of work to work this one out. But explain the situation that this is modeling, what kind of parameters define which of these you have. These are actually families of distributions for different values of the parameters, so tell what the meaning of those parameters is. Okay, this may take you a minute. Work this out yourself. Press pause. Come back. All right, so let's take a look at these. So a geometric distribution, an experiment is made where the outcome is classified as a success or failure. And the probability of success is always the same and is called P. So these are what are called independent Bernoulli trials with the same probability. The experiment is repeated until the first success occurs, and the random variable x is then the total number of trials. So notice there'll always be one success, the last one, and x minus 1 failures. What we don't know is how many times we have to repeat this Bernoulli trial until we get our first success, and that how many times we repeat it, that trial is x. So that's the meaning of a geometric. Notice it has one parameter that defines which geometric it is, and that's the number p. All right, a binomial distribution is also based on a Bernoulli, so it's got some similarities to geometric, but it's a little different. In an experiment, for a binomial experiment, we make, again, some Bernoulli trials where the outcome is classified as a success or failure. The probability of success is always the same and is called P. Again, independent Bernoulli trials with all the same probability P. But this time we know how many times we're going to do that Bernoulli trial. It's a fixed number of times, which we call lowercase n. We could call that either the number of trials or the sample size. And the random variable x is the other thing we don't know, the total number of successes. So you'll end up with x successes and n minus x failures. So notice that there are two defining parameters there, n and p. N, the sample size, and p, the probability of success each time. So one way we can get a binomial distribution is to basically have something that we're drawing from, say a finite population, and we're drawing from that. Then P is the proportion of successes in the population. But what we do is we put it back, mix it up, and draw out the second one. So the selection is done with replacement. Right? So the probability of success every time is P, the proportion of successes in the population. Now, hypergeometric is distributions are a variation on that. This time for hypergeometric, we have a population of capital N items that exist. Capital M of these items are considered successes. A sample size of lowercase n is selected without replacement. That's the difference in it and binomials, without replacement. So the random variable x then is the total number of successes. That's the same as a binomial, x successes, little n minus x failures. The difference is binomial is done with replacement, so that probability of success, the proportion of successes in the population is the same every time, whereas in hypergeometric, it is not. It's the probability of success each time depends on what came before, or success or failure. And the most important ones we're doing are binomial and hypergeometric, particularly as they relate to distributions of proportions. But we also talked a little bit about the Poisson distribution. X represents the number of occurrences of an event over time, where the occurrences are random, independent of each other, and uniformly distributed. And there's one defining parameter, which is the mean and the variance of the distribution. Is called either mu or lambda. And it's mu or lambda, whichever one you use, is both the mean and the variance of the distribution. And so you're basically doing these things where I said it's over time. It could be over some other variable, but oftentimes, most often it's time. All right, now what about the formulas that go with these? Can we write down the formula from memory for the PDF of each of these distributions, the formula for the mean of each distribution, and the formula for the standard deviation? Press pause and see if you can do this from memory. Well, here's what we get. For a geometric distribution, PDF of x is p times q to the x minus 1. This should make some sense to you here. Remember, q is 1 minus p, the probability of a failure. P is the probability of success. Okay, well, it's pretty easy. We always get in our tree, we always get a p for probability of success. And that happens one time, the last time. What we have is our one success. We have x minus 1 failures, so we have x minus 1 q's multiplied by the 1p at the end for the probability. The mean turns out to be q, or which is 1 minus p. And the standard deviation turns out to be the square root of p times q. Binomial distribution, we have PDF is n choose k, or n choose x, p to the x, q to the n minus x. So if you have x successes, you have x p's, and then n minus x q's multiplied together on one path, but they're n choose x of those paths through the whole tree that have the same number of successes. The mean turns out to be n times p, and the standard deviation turns out to be the square root of n times p times q. Now in hypergeometric, turns out to be like this. The denominator is big N choose little n. That is, you're starting with n things in the population, big N, and of those we're going to choose little n, the number in the sample. That's the denominator. And the top has two parts. The left part here is for successes, the right part is for failures, and they're multiplied together. So the part for successes is we take the m successes and we choose x of them. And if there's m successes and big N in the population, big N minus n, and m is the number of failures. And little x, that's in the population, and little x minus n is the number of failures in the sample. So we're choosing those failures from the failures here. So we're choosing x successes from a population of m successes. We're choosing x minus n, little n, failures from once again, this is the ways of choosing the successes. This is the way of choosing the failures, and this is the way of choosing anything. The mean is n times p, just like it is in the binomial, where p is the proportion of successes in the population. That's big M over big N. Of course, q is 1 minus p, and then the standard deviation is the square root of the npq, like it is in the binomial. But you got this extra factor that fixes for it being a hypergeometric instead of binomial. It's capital N minus lowercase n over capital N minus 1. The bigger capital N gets, the closer this fraction gets to 1. And then we have Poisson distributions. The PDF of x is e to the minus mu, mu to the x over x factorial. Some people put a lambda here instead of a mu. Same thing, but it is the mean, so I went ahead and called it mu. And the mu is also not only the lambda or mu is not only the mean, it's also the variance. So the standard deviation is the square root of the mu, square root of the mean. Okay, so that kind of wraps up these 5. We'll go do 5 more in the next video and 5 more in the video after that.